Get started. It is my pleasure to introduce Dr. Joshua Gonzalez, who is a postdoctoral fellow between the laboratories of Dr. Shea and myself. Dr. Gonzalez defended his dissertation last summer from Michigan Technology University, where he used multiple methods to examine the effect of acute fasting on the autonomic control of blood pressure at rest and during stress, work that I'm sure he'll touch upon during his talk today. As a postdoctoral research in our laboratories, he's integrating this prior training along with our tightly controlled multi-day human sleep and circadian experiments, both in the lab and in the field. Since joining our labs in September, Josh has really hit the ground running. Within a month of joining our labs, he was awarded the Oregon Health and Science University Fellowship for Diversity and Research. The fellowship supports salary, as well as provides a small budget to develop an independent project, as well as additional access to regular mentorship provided by the co-directors of the program. Dr. Gonzalez was also selected for this year's American Academy of Sleep Medicine's Young Investigator Research Forum and received the Society for Research on Biological Rhythms Emmett Chappell Award. I look forward to his presentation today and continued work over the next couple of years. And with that, Josh has noted that there will be a natural pause in his talk, which will be a good opportunity for questions. If you have questions, please note in the chat and I'll call you at that time to unmic yourself. And then again at the end. Thank you.
Thanks so much for that introduction, Nicole. Well, hello everybody. I'm going to go ahead and share my screen here. So the title of my talk is Autonomic Balance and How Fasting and Vaping Can Tilt the Scale. The agenda for today is I'm going to go briefly over the autonomic nervous system, a brief overview of the ANS, how we measure sympathetic and parasympathetic activity, what is autonomic balance, and then I'll go through two studies that I did during my PhD work on how fasting can influence autonomic control, and also how vaping on the Juul e-cigarette influences autonomic balance. And then I'll briefly cover at the end what we have planned for the future. And so my research during my graduate work focused on the autonomic nervous system. And the autonomic nervous system has two branches, the sympathetic, which is responsible for flight or fight, and that kind of sounds the internal alarm bells of our system. It dilates pupils, inhibits salivation, relaxes airways, and increases heart rate. All the things to get us ready to either fight or run away. The parasympathetic nervous system is for resting and digesting, and so it promotes salivation, stimulates digestion, promotes voiding of weights. Now, these two systems may seem like opposites, but they're more like contrasts or perfect foils. They're like Romeo and Mercutio, or Obi-Wan Kenobi and Anakin Skywalker. You know, one is the calming force, and the other one is the stressful force. And if there's an epic novel being written in your body, it would be about the autonomic nervous system. At least that's what I think. And the sympathetic nervous system gets kind of a bad rap because it's associated with stress, but an intact and responsive sympathetic nervous system is crucial. For example, if a fire alarm goes off, you want your pupils to dilate, to let in more light. You want your airways to expand, and you want your heart rate to increase to prepare you for high intensity movement and to give your muscles and brain the resources they need to react and escape the danger. In a less extreme case, the sympathetic nervous system is important for everyday activities like posture change, going from a sit to a stand. And because humans are upright standing bipedal animals with 70% of our blood volume below the heart, we need a sympathetic cascade whenever we just go through a simple posture change to keep our arterial pressure up and to keep our brain perfused with blood. And the baroreceptors play a major role in sensing pressure changes in our arteries. So when we go from a sit to a stand, the baroreceptors are offloaded and send signals that the pressure is dropping. So we need the parasympathetic nervous system can withdraw the influence over the heart and allowing the heart rate to increase. And then the sympathetic nervous system comes in and kind of applies the gas to increase heart rate maintain arterial pressure and maintain perfusion pressure to the heart. So having an intact and responsive sympathetic nervous system is important for quality of life, for day to day. We just don't want the sympathetic nervous system to constantly dominate because that's where we get into trouble. And so how can we measure autonomic activities? What are the techniques that we can use to investigate the balance? And so there's a couple. There's norepinephrine spillover, which is one of the most effective but is highly invasive. There's my favorites, which are heart rate variability and microneurography. Of course, there's catecholamines like epinephrine and norepinephrine and cortisol, which give a snapshot of general sympathetic activity. But I'm going to go into a little bit more detail into heart rate variability and also microneurography because those are the techniques that I will be talking about um, in the upcoming studies. And so our hearts are not metronomes. Each beat of the heart is fine-tuned by the vagus nerve that innervates the SA node. And so the vagus nerve releases acetylcholine, which binds to the SA node to reduce heart rate. And so the vagus nerve drives down heart rate. Without the influence of the vagus nerve, the heart would beat at its intrinsic rate, which is around 100 to 110 beats per minute. And so if you snip the vagus nerve, heart rate would go up. The vagus nerve modulates the heart on a beat-to-beat basis, and this can be seen in ECG waveforms um, by the time distance between each R wave. And so let me get a pointer. And so the time distance between each R wave is different and variable, and this is from the influence of the vagus nerve. And so if we plot these changes in R-to-R interval over time, the oscillations and variability become very evident. And then using a fast Fourier transform, we can identify the spectral power of the frequencies in these oscillations, giving us two physiologically relevant bands. The low frequency band is a little bit dubious, but it has been associated with sympathetic activity. And so the more spectral power that appears here, the more sympathetic influence over the heart, but the more reliable band is this high frequency band. The high frequency band has been shown to be a reliable indicator of vagal modulation of the heart, indicating greater parasympathetic activity. And so greater high frequency power is an indicator of greater vagal modulation of the heart, which indicates greater parasympathetic activity at the level of the heart. And so microneurography, which is used to measure muscle sympathetic nerve activity, is the gold standard assessment and only direct measurement of sympathetic traffic in humans. Microneurography involves inserting a tungsten microelectrode into the peroneal nerve at the popliteal or fibular head site. And once you insert into the fascicle, you get these beautiful postganglionic efferent uh, integrated bursts. And so if I could draw your attention up here to the blood pressure waveform, you can see that when blood pressure goes down, the nerve will burst, and when blood pressure goes up, there's a quieting or a quiescence of the nerve here. Uh, and these kind of go along with oscillations in blood pressure. And this is exactly what would help us or become active whenever we stand. This nerve would burst to increase resistance in arterioles, to maintain arterial pressure, and maintain perfusion pressure of the brain. However, overactivity of this system can lead to hypertension. And so that's where the balance becomes important. Balance of the autonomic nervous system is extremely important, and an overactive sympathetic nervous system is an identifiable characteristic of several cardiovascular diseases and other health conditions. This can be seen in chronic heart failure, in hypertension, type 2 diabetes, obesity, as well as obstructive sleep apnea or OSA. And I want to focus and show y'all how muscle sympathetic nerve activity responds during heart failure. So heart failure is associated with exaggerated and sustained sympathetic overactivity. The first neurogram here shows a normal control. So there you can see a couple of bursts happening. Also, keep an eye on the cardiac index, which relates to cardiac output in 1 minute to the bodice surface area. It's related to heart performance to the size of the individual. This is a neurogram in a mild heart failure case. You can see the bursts are becoming more frequent. They're also having greater amplitude. CI is dropping a bit. This is moderate heart failure. You can see the nerve is very active right now. There's a lot of activity. CI continues to drop. And then severe heart failure. You can see that the bursting is at 99 bursts per minute with a heart rate of almost of over 100. These are almost cardiac synchronous. And muscle sympathetic nerve activity bursts are gated to the cardiac cycle. And so once this becomes cardiac synchronous, that is the maximum output of this system, essentially. And MSNA is also an independent prognostic indicator of mortality. In this study, there was 122 heart failure patients were assessed by their survival rate, and patients that had over 49 bursts per minute had significantly lower survival rates than individuals with a lower muscle sympathetic nerve activity. And so what contributes to the balance? What activities promote autonomic nervous system balance, and which activities contribute to sympathetic dominance? Well, exercise training, good sleep hygiene, some pharmaceuticals like ACE inhibitors, and a normal BMI will contribute to autonomic balance. Chronic stress, sedentary lifestyle, poor sleep, smoking, and of course, a BMI over 30 will contribute to sympathetic dominance. And so, what we're going to look at today is how vaping and fasting contribute and where they land on this scale. So, let's start with fasting. So, in the United States, obesity is a serious public health challenge that has only become more prevalent through the years. And obesity is a chronic metabolic disorder that's associated with an increased risk of cardiovascular disease, stroke, type 2 diabetes, and overall mortality. Um, you can see as this progresses through the years, my home state of Texas gets more bad, but Oregon actually stays pretty good. They go orange there and then they go back to yellow. So good job, Oregon. I think the West Coast has a lower rate of obesity because of the severe lack in barbecue or really good barbecue, which Texas has. And so every year, about 4 out of 10 Americans go on a diet. And in the past 3 years, intermittent fasting and clean eating have jockeyed for the most common dieting strategy, with intermittent fasting taking the lead in the past year. And in 2019, a review in the New England Journal of Medicine highlighted the health benefits of fasting on health and aging and disease. And some of what was highlighted was that fasting, independent of weight loss, improves glucose regulation, insulin resistance. It can also stimulate autophagy or autophagy, which is kind of a buzzword surrounding fasting and is a homeostatic mechanism where the cell begins to remove damaged or unnecessary components. Intermittent fasting has also been reported to improve dyslipidemia and inflammation, as well as increase heart rate variability and reduce blood pressure and heart rate. However, this is chronic intermittent fasting. What about a fast just 1 day a month? Well, 2 observational studies conducted by the same group have demonstrated that fasting 1 day a month has been shown to be beneficial for reducing the incidence of diabetes and coronary artery disease. And the first study reported periodic fasting reduced participants' odds of coronary artery disease and diabetes. And then 2 years later, a follow-up study confirmed and expanded the association between periodic fasting in a new set of individuals. And displayed here is an odds ratio figure. And so anything below the 1 means that fasting reduces the odds of the outcome. In this case, that's CAD and diabetes. And anything above 1 would indicate an increase in risk of the outcome happening. And so you can imagine for coronary artery disease, tobacco smoke would fall into this red zone. And these results were adjusted for age, sex, BMI, hypertension, hyperlipidemia, smoking, and family history. And the meta-analysis suggested that the odds of diabetes was 43% lower in the infrequent fasters, and CAD was 42% lower in the infrequent fasters. And so it appears that even an acute periodic fast, as infrequent as once a month, may have beneficial health outcomes. And when we cease energy intake, or when we stop eating, we still need to meet our energy needs. And so we shift from utilization of glucose from glycogenolysis to fatty acid derived ketones. And the switch represents a shift from lipid synthesis and fat storage to fat mobilization in the form of free fatty acids and ketones. And the switch happens when glycogen stores are depleted and the liver are depleted, which takes approximately 12 to 36 hours after cessation of food consumption. It can be adjusted based on activity levels. And in the typical American eating pattern shown here, we would never really make this shift during the day. We have breakfast, lunch, dinner, maybe a snack. And so we're always infusing glucose into our system. There's really no need to switch over to using ketones. And so let's see what happens when we flip the switch. And so the purpose of this study was to investigate how an acute 24-hour fast influences ambulatory blood pressure, autonomic cardiovascular control, and neurovascular control of blood pressure. This was a randomized control crossover design with repeated measures. The two conditions were the fed condition, which was 3 hours postprandial, which is 3 hours after a meal, and 24 hours postprandial for the fasted condition. The meal leading up to the test was calorie controlled and identical between the conditions. The two sessions were separated by 4 weeks so that we could align our female participants' menstrual phase. And they were tested in the early follicular phase. To the right here shows the flow of the studies. Participants wore an ambulatory blood pressure cuff 24 hours leading up to the autonomic test. This was published 2 months ago. You can see the shout out to OHSU that I included in this figure, also my alma mater of Texas A&M and Michigan Tech. And so OHSU made it into the figure for publication. I'm going to go into greater detail into the autonomic test in this next slide. And so we took a lipid profile, measured glucose, ketones, and also got a measure of hydration status leading up to the autonomic test. Participants were instrumented with ECG and finger photoplethysmography, which is a non-invasive measure of beat-to-beat blood pressure, microneurography to measure muscle sympathetic nerve activity, and a pneumo belt. So during the autonomic function test, participants breathed at 0.25 hertz or 15 breaths per minute to a visual, and they timed their breathing to a visual stimuli. We have a previous paper that showed that the visual stimuli is much easier than an auditory metronome for individuals to pace their breathing. And then they performed 3 Valsalva maneuvers, breathing into this modified manometer, which I made for 15 seconds. And the Valsalva maneuver is an easily administered and reliable hemodynamic stressor that provokes both hypotensive and hypertensive stimuli. And the Valsalva maneuver reflects daily life activities such as straining or lifting, sneezing, or coughing in a reproducible experimental manner. So let's see what happens to heart rate, blood pressure, and muscle sympathetic nerve activity when we perform a Valsalva maneuver. So at the start of strain, interthoracic pressure increases, impeding venous return to the heart. And so blood pressure begins to fall, and the muscle sympathetic nerve activity begins to increase peripheral resistance. Upon release of strain, right here, venous return returns to the heart, blood pressure has an overshoot, heart rate will slow, and the nerve will go quiet. And so this allows us to assess baroreflex sensitivity during both the hypotensive phase 2 and the hypertensive phase 4. So 25 participants were recruited for this study. Participants were young, normal weight, and also normal tensive. Blood biomarkers were collected to ensure that they were fasting compliant and also to ensure that a 24-hour fast was a sufficient stimulus to initiate ketone production. Participants were weight stable and similarly hydrated between both conditions. We didn't measure any change in lipoprotein between conditions. However, blood triglycerides were significantly reduced in the fasted condition, as well as glucose was significantly reduced in the fasted condition. And importantly, blood ketones were significantly increased in the fasting condition, indicating that 24 hours of fasting was a sufficient amount of time to deplete glycogen stores and initiate keto production in our sample population. And so what happened with ambulatory blood pressure? Well, successful ambulatory blood pressure recordings in both conditions were made in 20 individuals. The average brachial recordings per day were above 30, and the night recordings were above 12. And so they far exceeded the recommended 20 and 7 ambulatory blood pressure recordings. And so fasting significantly reduced overall systolic, diastolic, and mean arterial pressure. Also, in the fasted condition over the 24-hour recording period, heart rate was also reduced, but this wasn't measured from an ECG. This was a recording taken from, the ambulatory cuff. And these reductions in overall blood systolic, diastolic, and mean arterial pressure were mainly driven by reductions in waking systolic and diastolic pressure. While it's not displayed here, there weren't any changes in the nighttime dipping patterns of blood pressure or nighttime blood pressure recordings. So overall, fasting reduced overall 24-hour blood pressure and heart rate. And so what about autonomic activity? Well, fasting increased the RDR interval, an indicator of gradal vagal activation. It also reduced heart rate during the autonomic test. Spectral analysis of heart rate variability was performed and displayed here as a representative subject, with the fed condition being in the solid line and the fasted condition being in the dotted line. And then I've demarcated the low frequency and high frequency component with this line. And so you can see in this subject that there's a clear increase in spectral power density in the high frequency component and a lower density in the low frequency component. You can also see this spike that happens at 0.25 hertz. And that's due to the breathing frequency. And that's why we control for breathing when we're doing this moment, because if we didn't, then it's possible that there'd be multiple spikes around where the participant was breathing. And then on average, for all the for the 25 participants, on average, there was an increase in the high frequency component of the spectral analysis of heart rate variability, indicating increased parasympathetic activity at the level of the heart. However, muscle sympathetic nerve activity didn't change, and so the direct measure of sympathetic activity in the periphery did not, while numerically lower, was not statistically significant. We also measured an increase in stroke volume, and this is from the pulse contour method. And so it's just an estimation of stroke volume from the blood pressure waveform. What was interesting about systolic blood pressure, however, was that while we didn't measure a change in systolic blood pressure during the actual autonomic test during controlled breathing, we did measure a reduction in spectral analysis of systolic blood pressure and the low frequency component. And I know I didn't go over this, but spectral power of systolic blood pressure is an indirect measurement of sympathetic activity in the vasculature. And so a reduction of this would indicate a reduction in sympathetic activity. And this is actually a helpful reviewer comment. They suggested that we run this analysis, and so we did, and it ended up being significant. So it was a great review. And so what happened with baroreflex sensitivity or cardiovagal baroreflex sensitivity? And remember that the baroreflex is a negative feedback mechanism that contributes to blood pressure homeostasis. While fasting significantly enhanced resting cardiovagal baroreflex sensitivity, the up-up sequence is important for dampening sharp increases in blood pressure. What the up-up means is that when blood pressure increases, the RDR interval also increases. And so the heart slows to dampen, to respond to that increase in blood pressure. And this occurs at rest. This was measured at rest during controlled breathing. However, the down-down baroreflex sensitivity, or the ability to withdraw vagoactivity to increase heart rate to a reduction in blood pressure, tended to increase in the fasted state, but didn't quite reach statistical significance. And so when we tested the system with the Valsalva maneuver, we did not measure an increase in baroreflex sensitivity during the phase 2, so the hypotensive phase, which corresponds with the down-down sequencing, but we did measure a significant increase during the phase 4 overshoot. And these two measurements, the agreement between both the resting spontaneous and also the assessment during the Valsalva maneuver indicate that fasting potentially increases spontaneous and dynamic baroreflex sensitivity at rest and during a hypertensive stress. So in conclusion, acute fasting reduces overall ambulatory blood pressure. It also reduces heart rate and increases heart rate variability, and acute fasting enhances cardiovagal baroreflex. And this is important because an increase in cardiovagal baroreflex has been shown in a previous study have reported that there's an inverse relationship between baroreflex sensitivity and 24-hour ambulatory blood pressure. And so the higher the higher baroreflex sensitivity you have, the lower your your 24-hour ambulatory mean arterial pressure is likely to be, potentially providing a mechanism to explain the observed reductions in overall blood pressure measured in our sample population while they were fasting. Okay, so where is fasting going to fall on this scale? Well, I'm going to gingerly place fasting as a behavior that contributes to autonomic balance. And the reason why I'm gingerly place it here because I think there's still room to investigate how fasting time influences autonomic activity. Too little and you may not get the effect, and too long may stimulate sympathetic activity to enhance mobilization of fat sorbs. But for now, the 24-hour fasting range seems to promote autonomic balance. And so I'm going to pause here for questions before I go into the e-cigarette portion of the talk. So if anyone has any questions about the fasting work, you could feel free to ask now.
Steve, you have a question?
I do. Thanks, Josh. That was really clear. I wonder if there are things that you didn't measure that could be causing the changes in blood pressure. I'm assuming that with fasting, there's an increase in circulating ghrelin, for instance, and that has been shown by others to decrease sympathetic nervous system activity. So ghrelin, the sort of hunger hormone,
Yeah, and so
decreases sympathetics.
Yes, and so what's interesting about ghrelin is that when you enter a fast, like a 24-hour fast, ghrelin will then go into a essentially a rhythm that is entrained to your habitual eating times. And so a study, I can't remember the name of the author, but a study has shown that when you enter into a 24-hour fast, ghrelin will peak at the times that you habitually eat. And knowing this study, this is anecdotal, but I would ask my participants when they felt the most hungry, and they would also say, well, the times where I typically eat, so like breakfast, lunch, and dinner, it was when I felt the most hungry. Actually, I have hunger score that they entered into an actigraphy watch that went off every 3 hours. I just haven't analyzed that data.
Okay, but what time of day were your studies?
They were between 10 and 2, and so basically the afternoon.
Okay. So sort of after breakfast, but maybe at lunchtime.
Yeah. And time wasn't a super constraint or wasn't really controlled for the study. That was before I joined the circadian lab and realized the importance of timing.
Okay, so it could be ghrelin.
Yeah, absolutely. Ghrelin could be contributing to what we observed.
Thank you.
I have a question about the, I guess the review paper that you pointed to at the beginning. What was the context of those studies, were they in just observations of naturally occurring fastings, or were they planned studies?
So for the New England Journal of Medicine review, that was a mix of animal studies and human studies. And so they throughout the review they would discriminate between this study was done in animals and this study was done, but they were experimental.
Because I had two parts that were related to that. One, I was just curious about what are the consequences of the next day? Is there an overshoot of maybe overeating, and what's the consequence of that? Or perhaps in preparation of knowing you're going to go on this fasting, is there a change in behavior? And then second, always I think thinking about how do you actually implement a health behavior change? What was the context there? I think about religions where there's often a fast, whether it's over a month or over a day or something like that. And is that something that's easier to implement than, say, a doctor suggesting that you fast for a day?
Yeah, no, those are excellent questions. So the study that pointed to the reduction in the risk ratio of, or the odds ratio of coronary artery disease and also diabetes was done in a religious group. It was done in the Church of Latter-day Saints, which promotes, 1 day a month fasting every single month. And so that specific, and they compared it to people that didn't practice that. And so that study was done in a religious group that was practicing fasting. And then you had another question. What was the first question?
About as far as like, do people overeat the day before or after?
Right.
Is that consequences of that? And that can
And
even
so
be studied in the animals. Do the animals overeat afterwards?
I'm not sure about animals, but so intermittent fasting has been shown to successfully reduce weight. And so if they were overeating to a vast extent the next day, then we you probably wouldn't see that reduction in weight loss if they're completely compensating for the day of fasting. That was a study. So it was a 12-week alternate. I had a slide on that, but I took it out. It was 12 weeks of alternate day fasting. So fasting for 24 hours one day, eating whatever you want the second day for 12 weeks, and there was a reduction of about 8 kilograms in total body mass. And what was interesting about the study is that they didn't have a significant reduction in fat-free mass, and so muscle seemed to be maintained, and fat was really the one that contributed to the reduction in body mass. Those are great questions, though.
Matt, I don't know if you meant to, I think you probably meant for your question to go to everyone, right?
Yes, it was
Yes,
supposed to go to everybody. So the question is, does the blood pressure go up or down with normal eating, like in a postprandial state? And would that be enough to influence your ambulatory blood pressure measures that you saw? Either, did it actually make it smaller or did it make it bigger?
That's a really great question. I'm not sure how. So of course, when you eat, there's going to be a big, uh, kind of your blood is going to be diverted to your digestive tract to assist with digestion. I do know that eating a meal will increase sympathetic activity like muscle sympathetic nerve activity to compensate for that diversion of blood to the gut, essentially, to increase peripheral resistance. But I can't remember what it does to blood pressure, and that's why we chose the 3 hour postprandial mark for the Fed condition, because that's when uh, muscle sympathetic nerve activity comes back down to baseline from the meal. But that's an interesting question to look at the ambulatory data to see if there's any patterns in if blood pressure patterns in blood pressure that correspond with their meals.
Great, thank you.
Well, I have one other more comment, perhaps, but thinking about Oregon and where there increased but then decreased in 2016. 2016 also coincides with, I believe, the legalization of recreational cannabis. And so while cannabis may temporarily increase munchies, it's not associated with an increase in weight gain. So it's interesting to see that actually things decreased after that time point. So clearly just a correlation, but interesting nonetheless. So yeah, please continue.
Yeah, I did pay more attention to that map now that I'm in Oregon. I was like, wow, Oregon, really kicked it in. They went back down. No other state really goes back down. Okay, so we'll continue on to e-cigarettes. And so a brief side note is that I thought the e-cigarettes would be my PhD path. I don't know if there's any grad students on this seminar, but if there are, this is essentially for them. However, in 2019, we got hit with a valley or e-cigarette or vaping use associated lung injury. And at the time, there wasn't really enough information to know if what we were asking participants to do was safe. And so we halted the research then. And then once we found out that it was THC contained vape products with a synthetic form of vitamin E that was causing the issue, we proceeded, but then right around the corner was COVID-19. And so I pivoted to fasting, which is something that can be done while wearing a mask. And so the e-cigarette was what I started with, and then it fell off. And so I want to start off with talking about how tobacco cigarettes influence sympathetic activity. So tobacco cigarettes are a leading cause of preventable cardiovascular disease still in the United States. And tobacco smoke stimulates sympathetic activity, which drives up blood pressure. In individuals with an intact barrel reflex intact barrel reflex and responsive barrel reflex, uh, the the um, the barrel reflex will act to inhibit sympathetic activity to try to drive down blood pressure. And people with intact barrel reflexes are young, healthy people. And chronic smoking of tobacco cigarettes will slowly impair the barrel reflex. And if you have an impaired barrel reflex and you smoke a tobacco cigarette, the brakes are essentially broken. And so there's no brake on the increase in sympathetic activity. And so then it just drives up blood pressure. And tobacco smoke can causes sympathetic overactivity in two major ways. Fine particulate matter less than 2.5 micrometers, and a micrometer, your hair is 20 micrometers, and so very, very small, can generate inflammation and also oxidative stress, and that can impair the barrel reflex. So that's damaging the brake on sympathetic activity. Additionally, particulate matter can stimulate lung afferent C fibers, and afferent fibers reflexively increase sympathetic nerve activity. And of course, there's the nicotine. There's that lung afferent line. And then, of course, the nicotine, which can directly interact with the RVLM to increase sympathetic outflow while reducing the availability of nitric oxide. So in short, tobacco cigarettes step on the gas and damage the brake when it comes to sympathetic activity. And this became really concerning as essentially nicotine use became renormalized in young individuals. And while a majority of e-cigarette users are smokers trying to quit, about a third of users are former smokers picking up nicotine again or never smokers. And even more alarming was the increases that we saw in the 2010s. And so the increase seen in youth e-cigarette usage in 2018 negated the previous decade's decline. This is any tobacco product use for high schoolers, but the increase in 2018 negated the previous decade's decline in any tobacco product use, and this was driven by the uptick in e-cigarettes. However, the pandemic hit, and high school and middle schoolers are now at home with their parents, away from classmates. And so e-cigarette use among high schoolers peaked in 2019 with almost 28% reporting current vaping use, and that's like use within the previous month. And in 2021, it dropped down to 11.3%. And so a massive decline, but likely a temporary one. E-cigarettes still remain the most used tobacco product. I know this is hard to see, but this line is the e-cigarette line. Um, it's still the most used product among high schoolers out of all the tobacco products and middle schoolers. And this was really driven by the rise of the Juul e-cigarette. And so with that same peak in 2018, 2019, the Juul e-cigarette captured almost 75% of the entire e-cigarette market during that time. And it's still and e-cigarettes like the Juul and the Juul remain the most used e-cigarette. They're classified as disposable e-cigarettes because it's the pod, you can just throw it out once you're done with it. It's still the most popular among young individuals. And so our study was to specifically we conducted our study to specifically focus on the Juul e-cigarette. And so this study, we had a 10-minute baseline, a 10-minute vaping protocol with 20 inhalations, and a 10-minute recovery. And participants again breathed in time to that waveform I showed earlier at 15 breaths per minute throughout the experiment, and were prompted when to inhale on either the on the e-cigarette. And again, this was a randomized controlled crossover design with the Juul e-cigarette being the e-cigarette with nicotine, and a similar Juul e-cigarette with the same non-nicotine constituents in the e-liquid, just without the nicotine. And so we measured muscle sympathetic nerve activity, beat to beat blood pressure, ECG, and you can see kind of our setup here with the laptop with the breathing program on it, and they're in a semi-recumbent position to inhale on the Juul. We put 15 young normal weight individuals through this protocol, and what we found is that the black bars represent vaping on the Juul that contains nicotine, and the gray bars indicate vaping on the Juul without the nicotine. But again, it has the same non-nicotine constituents, the vegetable glycerin and the propylene glycol. The Juul with the nicotine increased mean arterial pressure, drove down muscle sympathetic nerve activity, and increased heart rate when compared to the placebo e-cigarette. And the increase in arterial pressure, the reductions in MSNA, and the increase in heart rate held throughout recovery. And so you can see in these neurograms over here, this is the nicotine group's baseline, and then the nicotine or their neurogram when they're actually using the device. And so you can see in this individual quiescence of the nerve as their mean arterial pressure increases, and this held for these other example participants in their neurograms. And so what was striking to me was the parallels to the, and this figure, which was in the paper, was my homage to the 1990s work done by Niedermeyer with tobacco cigarettes using a similar protocol. And the blue bars here are the baseline, is during baseline. The red here is during active use of the nicotine product, and the gray is the recovery. And so this is R-to-R interval, and I'm displaying heart rate, and so these would be inverse. And so I just wanted to draw your attention to the parallels that we see here, and within these two similar protocols, the increases in systolic blood pressure, and then also the reductions in muscle sympathetic nerve activity. And of course, these are two representative individuals. And so, in conclusion, acute use of the Juul e-cigarette increases heart rate and blood pressure, which then inhibits muscle sympathetic nerve activity, likely due to baroreflex inhibition. And to continue building evidence of where to place vaping on the scale, this study was using a similar e-cigarette with nicotine, e-cigarette without nicotine, and then a sham control design. This is looking at heart rate variability, and they demonstrated a significant decrease in the high frequency component, and so greater vagal withdrawal from the heart when participants used an e-cigarette with nicotine. And this next study was published last month, which is pretty cool because they replicated my results in that they used a tobacco cigarette, a sham smoking, and an e-cigarette. And here's mean arterial pressure, and you can see how blood pressure increases with both the tobacco and e-cigarette. And this is muscle sympathetic nerve activity over here. You can see similar declines in muscle sympathetic nerve activity during the use of the tobacco cigarette and the use of the e-cigarette. But what was really cool about this study is that they also measured skin sympathetic nerve activity, which we can measure using the same microneurography technique, but just with an adjustment to the style of which we're probing for the nerve. Skin nerves are much more shallow than the muscle nerve, which is deeper. But what's interesting about skin sympathetic nerve activity is that it's not inhibited by the baroreflex, and so it just goes up if there's something that's triggering an increase in sympathetic activity. And so you can see here with a tobacco cigarette that there is an increase in skin sympathetic nerve activity as well as with the electronic cigarette. And so where to place vaping? I would place vaping in that it's a behavior that's going to contribute to sympathetic dominance. I mean, you're going to turn it red there. And so for a future direction, like Nicole had mentioned, I still feel pretty fresh to circadian and sleep research. I think this is my 8th month as a postdoc here, but there's been interesting reviews that have come out looking at sleep as a target to try to optimize smoking cessation treatment, as well as the work by Dr. Bowles investigating how cannabis use can affect sleep. And there's been a recent buzz surrounding the use of cannabis in the treat as a sleep aid. Essentially, I think this was published in 2020. And that led to the future direction, the study that we're really exciting about, which is called Cosmos. The goal is to investigate the impact of chronic cannabis and nicotine use on circadian phase, looking at dim light onset melatonin and also sleep patterns. And we've added in those autonomic tests that I've mentioned in my previous studies, looking at controlled breathing and also the Valsalva maneuver, as well as measuring the autonomic response to social evaluative cold pressor. The cold pressor test sends sympathetic activity through the roof and blood pressure. And so I'm really excited to measure in these chronic users what their baroreflex sensitivity is and how that translates to the sympathetic activity and blood pressure responses seen during the stress. And so we plan to measure circadian phase and evaluate sleep patterns in chronic cannabis users and chronic nicotine users and determine how chronic use of these substances influences autonomic balance. And so there is a lot more to investigate with the autonomic nervous system, with cannabis and nicotine cessation and sleep, as well as with circadian rhythms. And so I think the future is very exciting to apply autonomic research methods and merge them with sleep and circadian physiology. So I can take any questions. That's about any part of about the presentation, fasting or e-cigarettes.
I was not raising my own hand. I meant to give claps as well. Uh, any questions?
Also, in the spirit of human research, I put myself through all my protocols, and I would say like the vaping was definitely worse than the fasting protocol.
I was gonna ask, was that you in that picture?
No, that wasn't me in that picture. That was a fellow grad student who was nice enough to model.
So I hadn't realized that for the vaping that the conclusion was that I mean, I heard a little bit that there was some pointing to the THC vape being the cause. But I thought it was still questionable questions regarding vaping in general, and in terms of the chemicals that are that people are exposed to, especially the flavorings. I think more than anything that there are some of those chemicals that are still part of some of the flavors, and I forget the exact ones. But then COVID did happen, and there were bigger concerns. So is there any ongoing research that digs into that a bit further?
I know there's definitely ongoing research. I'm just not up to speed on it. Investigating how. So like I mentioned that tobacco cigarettes are one of the ways that they stimulate sympathetic activity is through the production of particulate matter, which is a product of the combustion process of tobacco cigarettes. And so I think there's been an increase in the interest in looking at how vaporization of the non-nicotine constituents as well as nicotine, if they're producing particulate matter that is able to stimulate lung afferents and increase sympathetic activity. But looking at the valley, that outbreak where there was a very acute, fast acting damage that occurred in the lung, that was kind of traced back and isolated to like a single e-liquid producer that was putting that synthetic vitamin E into the liquid, and when it was heated and vaporized, it became extremely harmful to lung tissue. But I know that chronic use of e-cigarettes and their effect on the lung is an ongoing and very active scientific inquiry.
All right, well, if there are no